Howdy, folks. That's all. I don't have anything else. Just howdy, folks. So let's see here. Where are we? We are trying to get ourselves together. All right. We are looking at the force that a magnetic field exerts on a current carrying wire. And we've got our equation. It says that force is equal to current times length times magnetic field times the sine of the angle between our current and our magnetic field. All right. And here we are faced with a problem. It says we've got a wire that's got current running through it. And we're given the length of the wire. We're given the mass of the wire. We're given the current in the wire. And we're asked to figure out what is the minimum, it's easy for me to say, minimum magnetic field strength that will allow this wire to basically float. All right, so let's get started on answering our problem. What's the first step? Draw a picture. Can't believe nobody answered me. So there's a wire. Wire. Okay, and we want this wire to float, right? So let's see here. Maybe some grass down here. There's the grass. There we go. So there's the ground. All right. And then let's see, maybe we better indicate the direction of the current in the wire. Maybe the current's going that way. And we're told that the current is 2.4 amps. And while we're at it, since I'm writing stuff down, we're told the length here is 0.2 meters. And we're told the mass is 5 grams, but of course, we don't operate in grams, right? So that would be 0.005 kilograms. All right. Back to the picture, I got distracted. Let's see. What might be good to put on our picture? Forces. So let's see. We're going to have a downwards force due to what? Due to weight. Use your imagination. That says weight. And then we've got to have an upwards force that will balance the weight in order for this thing to levitate. And that upwards force is going to come from magnetic field. Well, that's the premise of the problem, right? So we're told that we have to sketch this. It says at the last sentence, sketch something, the scenario for the problem. So that would include the direction of our magnetic field. That should be included in the sketch. So let's see. If I'm sitting at home staring at this, the current, as I have it drawn, is going to the right. So I'm going to put my fingers to the right. My palm should be facing the screen here. Why? Because I want the right-hand rule to work so that I've got a magnetic force that's upwards. My thumb has to be pointed upwards. And the right-hand rule says that my fingers point in the direction of V, and then they will curl in the direction of B. So curl in the direction of B. And then based on this, this will determine the direction of my force. Well, that would be if we had the direction of the magnetic field. But in this case, what do we have? We've got the direction of the force. That's my thumb. We've got the direction of the current. That's the fingers. They should be pointed to the right. And then your hand should be curling into the screen in order to produce that force. If I try to do it the other way to get an upwards force, well, now my fingers are pointed in the wrong direction. My current's going to the right, not to the left. Right, so again, this is weird because the camera's mirrored and so on and so forth, but hopefully you're following along at home. All right, so I probably should indicate here the direction of the magnetic field. There we go. Magnetic field is into screen. All right. So awesome. One other thing this says is we're supposed to be figuring out the minimum magnetic field. Well, why is that important? We'll see in just a moment. In order to get this thing to balance, to levitate, my forces have to be balanced. That's what I intended to say. The force due to magnetic field on a current carrying wire is ILB sine theta. Weight, we know this from last semester, is mg. I've got what? I've got the mass, I know what small g is, I've got current, I've got L. I don't know B. I don't know the magnetic field strength. That's what I'm trying to solve for. And I don't know theta. Of course, we're supposed to find the minimum magnetic field necessary. If I want to minimize that magnetic field, the best way to do it, well, the only way to do it, is to orient the wire so that the magnetic field and the wire are perpendicular to each other, so that theta is equal to 90 degrees. So that being said, I can go ahead and rearrange my equation here. Mg over ILB sine theta. When I plug in numbers and do the math, I should get the result that the magnetic field strength is 0.102 Tesla. And according to the sketch that I've drawn out here, that would be into the screen. All right. Of course, if I had drawn the wire going the other direction, then that would have resulted in a magnetic field that's out of the screen. If I had tried to draw a wire that was maybe vertical, then this whole thing isn't going to work, because I need a force, a magnetic force that's vertical, and magnetic force is always going to be perpendicular to the direction of the current. So that wouldn't work out. That's why I have to draw the wire so that it's horizontal. So is this realistic? Is this a realistic problem? Well, 0.1 Tesla is a really strong magnetic field. So maybe not. I will say that I've done this experiment in lab where I've definitely noticed a decrease. So I put the wire on a scale and definitely noticed a decrease in the reading on the scale when a magnetic field is applied. So that definitely happens. Also, this idea is used in modern technology, and you guys know of it too. So you know those LEV trains. So those levitation trains, magnetic levitation trains that maybe in China and Japan, yeah, they operate off of this same kind of principle. All right, so that was an awful lot of talking, but I've got some more coming. Let's see, we got another example problem here. We are staring partially at the inside of a speaker. So we've got a speaker, or we've got maybe an earbud. An earbud, of course, has a speaker inside of it, very small speaker, but works based off of this kind of technological idea. We've got a speaker that's a speaker cone that has some wire wrapped around the base of it. So there's wire wrapped around right there. Let me change colors. And that is basically inserted into kind of an odd shaped magnet, which is right there. And then based on the current that runs through the wire, you know, let's see, we get a signal from our, I don't know, our stereo system, whatever, MP3 player, whatever. That, you know, we've got current running through this wire. Current running through the wire interacts with the magnetic field from the magnet, and as a result, what happens? That magnetic field exerts a force on the wire, and that force will vary based on the current, and will also cause this entire speaker cone to move back and forth. And we learned earlier this semester, in January or February, that when we've got a speaker cone or a speaker that's moving back and forth, what are we doing? We're creating variations in the air pressure and we're creating basically traveling sound waves. This ties into what we learned earlier in the semester. All right, we're given a bunch of numbers here. We're asked to figure out the magnetic force that is exerted on this coil of wire based on the magnetic field. So we've got a magnetic field there of 0.1 Tesla. Maybe just go there, 0.1 Tesla. We've got a current of 2 amps. Let's see, if I think about the F is equal to ILB sine theta equation, I've got magnetic field, I've got current, length of the wire. So I would need to know the length of the wire. Well, this particular wire is wrapped around in a circle, and it's wrapped around in a circle basically 55 times. It makes 55 circles. What's the circumference of one circle? Well, the circumference of one circle, maybe let's see here, spell that out. Circumference is what? Pi times the diameter. Of course, what do I have? I've got 55 of those. So 55 times pi times the diameter, which we have, it's right up there. Will give me the length of the wire that I have. So great, now we've got L. The only thing we don't have now is this theta. So what is theta? And let's think about that for just a minute. All right. So this speaker cone, or this part, is going to get inserted into this peculiar shaped magnet. And I can look at the directions of the magnetic field around this magnet. So at the top of the magnetic field is going to go up. Magnetic field always starts on north poles and goes towards south poles. At the bottom, it's going to go down. Again, magnetic field starts on north poles, goes towards south poles. Well, let's think about the direction of the current at the top of this coil. At the top of the coil, the current is going into the page. So I is into the page. And now let's think about our right-hand rule. Current's going into the page, and the magnetic field is upwards. Oh, my fingers have to curl upwards, so my palm better be facing towards the ceiling as I'm trying to figure this out. So fingers point into the screen. So if I'm sitting here watching this, fingers point into the screen, magnetic field goes upwards, my thumb is pointing to the right. So the direction of the force, at least at the top part of this coil, is to the right. All right, let's look at the bottom of this coil of wire. At the bottom, it looks like the current is coming out of the screen. So current's going out of the screen, coming towards you. And again, think about the right-hand rule. Current's going out of the screen, my fingers should be facing my face, basically. And then the magnetic field is going downwards. Okay, so I curl my fingers downwards and my thumb is pointing to the right. Okay. So the force is also to the right. And if I think about maybe the front of this coil, I can do the same kind of right-hand rule. I think about the back of the coil, I can do the same right-hand rule. That's good. All of those places are going to give me a force that's pointing to the right, which is fantastic. The other thing is, well, what is theta? Well, if we look at the top of this coil, the current is going in and the magnetic field is up. That theta is going to be 90 degrees. So theta is equal to 90 degrees. All right. Now it seems like we've got all of our parts of our equation checked off. So let's take a look at the actual calculation that happens. All right. First, here's a schematic of basically the coil and the magnet all placed together. So if you had a little bit of a problem visualizing maybe what I was saying on the last slide, hopefully that schematic might help out a little bit. For instance, up at the top, right there, we've got current going into the page and then magnetic field upwards. Current going into the page, magnetic field upwards, gives me a force to the right. And then, with the bottom, okay, force to the right again. Okay, so let's take a look at the calculations. Okay, well, there they are. I've got F is equal to ILB sine theta. I plug in everything that I pointed out on the previous slides, and I get a force of 0.086 newtons. Part B of this problem asks for the acceleration of the speaker cone. Well, we know force is equal to mass times acceleration. So if we just divide the force by the mass of the speaker cone, we'll get the acceleration. The acceleration is 4.3 meters per second squared. All right. If we think about the signal that's coming from the stereo, that signal is going to vary based on what sound basically based on what sound the broadcasting is looking to play. So, you know, music is made up of all different frequencies. The amount of current as well as the direction of the current is going to change. So that force that exists on that speaker cone is constantly going to be fluctuating. It's not always pointed to the right. Sometimes it's pointed to the left based on the direction of current. But it's those fluctuations that actually end up causing fluctuating signals for our speaker cone, fluctuating forces that actually produce the richness of sound that we can hear from speakers. All right, lastly, so this is a neat application of current carrying wire with magnetic fields. We also saw another one, the magnetically levitating trains. One more is this idea of water propulsion with magnetic fields and current. I'm not going to get into that, but if you're interested in reading about it, there's a link right there at the bottom. This is magnetohydrodynamic drive, so you can look that up as well, which is I think a pretty cool, although not all that realistic application of magnetic force on current. All right, we'll talk again soon.